The 17th inaugural lecture of the University of Moratuwa. With the honors of introducing our inaugural professor for the day, lecturer, Prof Chinthaka Mallikarachchi, I wish to invite Emeritus Professor Prof Chinthaka.
Thank you very much for giving me this opportunity to introduce Chinthaka. I first met Chinthaka Mallikarachchi, or got to know him actually, when I was looking for someone to do some computer modeling on a small consulting project that I was involved in. So I couldn't find any among the younger members of staff because they were busy or otherwise occupied. And Chinthaka's supervisor, Dr. Kirti said that maybe you can take a chance on him. He was a final year student at that time. And Chinthaka proved to be very meticulous and committed to his task, and assisted me greatly in doing the computer modeling of this building, which had developed some defects and we needed to find out why those defects were occurring. This relationship with computer modeling is something that has characterized our relationship over the years, including doing the model for the Lotus Tower, which Chinthaka did with great competence, because he had to develop the model for the Lotus Tower without getting it from the Chinese designers who were not willing to give it to us. But his model, we were able to compare the outputs and they matched very closely with the Chinese outputs. And more recently he was involved in designing involved in retrofitting of a water tank, where once again he had to model the expected behavior. So later that year in 2005, the joint board of moderators were visiting our department, and Chinthaka once again as a final year student had great maturity to sort of make a kind of liaison between the team and the academic staff members. He communicated to us some of the concerns that the joint board of moderators had, and it helped us in our response. So soon after he graduated, of course, I invited him to be a research assistant on a SRC grant, which some of you know about, and I was only learning about about tsunami loads and resistance, but I don't know how well I guided him, but anyway we were able to get a paper in the structural engineer journal. Now around this time, he was thinking of postgraduate studies, and a few students in the previous years had been successful in going to Cambridge. We had a long drought, and then about 2 or 3 years there were people who had gone to Cambridge. So I wrote him a reference. I remember writing that although Chinthaka graduated 4th in his batch, that I would rate him first. That may have been a sort of, personal opinion. And I don't know how well that helped him to get to Cambridge, but a few years later when I met his supervisor, he told me that one of Chinthaka's references did in fact say that, although he was 4th in the batch on graduation, that he was rated first. So I'm very happy that he was able to go to Cambridge. When he was there, because his supervisor went to the California Institute of Technology, I think Chinthaka had to take a decision whether to remain at Cambridge and finish there or go to Caltech. As it is, he went to Caltech, and although he didn't transfer his registration, a lot of time he spent at Caltech. And I think this gave him the best of both worlds in terms of UK as well as US experience. And I think this is something that he has brought to bear in his career. So around this time I was head of department from 2007 to 2010, and it so happened that I was able to visit the UK during that time. I don't know how many of those times I met Chinthaka, but I actively headhunted him to come back to the department. I remember once having tea with him at the Paddington station. I'm not sure whether he remembers that, but fortunately in 2012 Chinthaka did decide to join the staff at Moratuwa University, and I don't know, maybe you can say the rest is history, because in about 10 years now he has become professor. I would like to read to you about his career from something I wrote as a reference for his Fulbright fellowship. I have said throughout his career he has chosen to remain in technologically advanced research fields, something that very few Sri Lankan engineering academics have done. He has in parallel been able to attract the best and brightest of successive student cohorts to work on his projects both at undergraduate and postgraduate levels. This has resulted in no less than 7 of his students going on to Cambridge University for their own PhD studies, 3 to Caltech, and 1 to the University of California at Berkeley, and many other places as well. This is just to mention what I consider to be top places. A truly noteworthy achievement in the span of 10 short years as an academic. Even more impressive is that 1 or 2, depending on the way you count, of the above have also returned to this department as faculty members after their own PhDs at Cambridge. So, I would think that Chinthaka has fulfilled the promise that he showed as a student and a young academic. I am aware that he has got many research grants through the Senate Research Committee and also through the National Research Council, because I have sat on both of these bodies. He has got awards in plenty, including the Raghu Chandrakirti Gold Medal from the Society of Structural Engineers. And he has also, his collaboration has been sought by professors from Indian Institutes of Technology at Roorkee and Hyderabad as well. In the middle of all of this, I'm sure all who know him will agree that he remains a very unassuming person. In spite of his impressive research credentials, he pulls his weight in teaching in the department. I have left the department for about 2 years, but I'm sure that is the case, and also in administration. I would just like to sort of wish him well. I'm sure that we will be treated to an excellent lecture about the topic that he has chosen to speak to us about. I wish him well also in his Fulbright fellowship, which he has now obtained, I think. So let me invite Professor Chinthaka Mallikarachchi to deliver this inaugural address.
Thank you very much, sir. It's an honor to get introduced by yourself, and probably I'll refer to that towards the end of my presentation. Vice Chancellor, Deputy Vice Chancellor, Dean Faculty of Engineering, Dean Faculty of Graduate Studies, all other deans, Head Department of Civil Engineering, all the heads of departments, my dear colleagues, students, family and friends who are here as well as joining online. It's indeed a pleasure to do this inaugural lecture, and I would like to thank Prof Ajith de Alwis giving me an opportunity to forcing my teachers to listen to me as well as my family as well. Being a little child, I was always looking up to my father and wanted to become an engineer. I didn't know what are the subjects I had to take and whether you have to take maths, chemistry and physics for the A-levels, but just to become an engineer simply because my father who was an engineer. So that inspiration from my childhood led me today to the journey beyond gravity. So just by looking at the title itself, you would probably have 2 questions. First, isn't beyond gravity is easy because it's one less equation to solve, so it should be easy. And then the second, what does the civil engineer doing in space? Because as far as most of us are aware, civil engineers has to ground somewhere so that the structures has to transfer the loads. So in a little bit, I'm going to explain you why this happened and what are the reasons and why I ended up here. So hopefully during this lecture, I'll be able to give you some answers as well as maybe inspire some students. So get back to answer the second question. Basically my research is focused on aerospace structures as title depicted, and also I'm working on the civil engineering structures, large structures, mainly computer modeling and similar areas. So today I would like to focus on the space structures part of it, and in fact Professor has introduced certain things that why I ended up here, but at the same time this is the exact structure that led me to apply to Cambridge, because this is actually, I saw this on website and it's a retractable roof, so I thought it would be interesting as a civil engineer to look into. But of course when I went there, my supervisor said there are these other avenues, that's how I ended up here. Right, I was privileged to have experience of, in a way, best of both worlds. Both these institutes are ranked top 10 in the world, wherever you look at, whatever the ranking you look at. Cambridge, of course, has over 800 years of academic excellence. And Caltech owns NASA JPL, the Jet Propulsion Laboratory, which sends the Mars rovers to Mars. And also it had the wind tunnel in the California region. All the aeroplanes were built in, manufactured in west coast of USA, were tested in this particular lab. So because of that, both these basically sort of helped me as well as nurtured me into this area. So getting back to the topic, hopefully at this end of the presentation, I would hope that you would understand what the space structure is, and I'm going to talk about what are the design challenges, change in environment, transport and energy demand in space structures, and I will try to use a case study where I will sort of walk you through how design process would be and how you would approach it, and finally I will end up with a couple of future applications and acknowledgements. So these are some of the iconic space structures, I would say. So people who were born in my time or before probably remembers this Mir space station. So it used to be the only space station available, and it's mainly a Russian one, and recently it was replaced by the International Space Station, jointly launched by several countries together. And then when it comes to telescope, Hubble telescopes used to be the one which dominated the world, and last year the James Webb telescope replaced that, and now they are looking into even further as well as galaxies as well as the planets and whether there are any habitats. And this Icarus solar sail by the Japanese Aerospace Agency, which I will come back to that, is sort of a step in future where they went into a larger solar sail. What is a solar sail? I'll get back to that in a couple of slides. And the Starship project by the NASA is another example that I'll discuss. And I'm sure all of you are familiar with these Mars rovers. So they are the NASA, especially the Jet Propulsion Laboratory, is exploring the Mars surface as well as subsurface conditions. So let me take an example, a solar sailing as an example to explain these what are the space structures I'm talking about today. Solar sailing is analogous to wind sailing. Basically, photons emitted by the sun is hitting a sail or a membrane and get reflected, and that provides a propulsion to propel the aircraft. So this requires large surface area because the amount of energy you are gaining is very less, so you need a significantly large area. So because of that, the relative size is a bottleneck. Now, if I give you an idea about what we are talking about, this is an example of NASA solar sail. One of the solar sails is 160 meter by 160 meter, and that has to be packed into one of these spacecrafts. But if you can't imagine, if you're not familiar with the Washington Monument, let me put in prospect to Sri Lankan conditions. So all of us know Colombo Lotus Tower. We are talking about half of the Lotus Tower, and in fact, it has to fit into not the launch vehicle, but the storage component of the launch vehicle is only a very small amount, because most of these things is for propulsion, and that will basically send off electrons. So now somehow we have to pack this large configuration into a smaller compact stage, and this is an example where they are trying to explore or expand. So basically, essentially what we are saying is you need some sort of a deployable structure, which basically the research topic I'm presenting today, and that has to be light in mass and easily compactable for launching or basically sending out of space, sending from Earth. Now, what are these structures and how you look at it? You always you look for nature and naturally inspired. So what you're seeing here is a blooming moonflower. I'll come back to that later on. This is recently used by NASA for one of the projects. So as you can see, when the flower is blossoming, it rotates and goes around and suddenly pops out. So these concepts are being in nature, and then you can make use of this. So as I said, these structures need a large surface area or volume when they are in operation, but it has to be compacted to much smaller configuration during storage and transportation. So what are these structures, and we call deployable structures, and the simplest day-to-day example that all of us are familiar is an umbrella. So you can keep the umbrella in your handbag or maybe in your pocket, and then when you're out, whether it's sun or rain, you can easily expand. But if you think of the structural point of view, there are two extremes. One, it has to be soft so that it can bend and compacted. But at the same time, when it's in operation, it has to be stiff. For example, when you are holding an umbrella in rain, and if the rain droplets collapse the umbrella, then the operation is lost, right? There's no use. So because of that, these are two extreme cases in structural engineering you have to be looked into. And then the other problem here is if you think of an umbrella, you have to basically use your hand and push it out. So if you think in space structures, you have additional motors and also the energy source to deploy. That means you have more mass, more weight and more volume. So it's very difficult to send it out, so it becomes another bottleneck. Whereas if you look at the umbrella itself, nowadays there are umbrellas which you just press a button and it self-opens. So if you can make use of this, you can basically remove all these mechanical components as well as a requirement of energy in the long run. So these are called self-deployable structures. Simplest day-to-day example is a carpenter tape. So I'm sure all of us have used this carpenter tape. If you pull it out and then release, it will coil back. So in space, what you need is the operation in reverse. So these are some of the self-deployable structures that has been used. So if you look at this Boeing spring rack reflector, you can actually see the Canadian flag through it. So it shows how lightweight it is, and also these are compacted into different configurations. So there are different examples. This is actually developed at University of Cambridge. So this small part, once you release it, comes back to this. Is the 1/16 scale of the actual structure that they intended. And similarly, there are other examples from European Space Agency and some other places. And then today I'm going to focus more on what we call a deployable boom. So what you're seeing here is an example of an actual mission by the European Space Agency sent in 2006 and 7. The mission here is to look at whether there are subsurface water paths or water in Mars. So in order to do that, they had these antennas. There are three poles. If you see, two dipoles, each having 20 meter long in length, and a monopole with 7 meter length. So you cannot fit into this 40 meter long boom in a spacecraft. So the idea is to somehow compact this and put it into a 1.7 meter cradle as shown here. So the concept they came up with, you slot this at certain intervals and you fold it here and then put it there. So once you go into space, once the clamps are released, this has to automatically deploy, so that you don't need additional mechanisms and the power to deploy. And this is another example where the German Aerospace Agency is using two omega-shaped cross sections together, glue them together. So you will have a circular or omega-shaped section here, and then a flattened and coiled. So the idea is once you go into space, you release the clamp, it will deploy in a radial direction like this. And here you are seeing how they are going to, or how they are planning to deploy a 20 meter by 20 meter sail with 4 of these booms. So there will be 4 booms compacted at this point, and those will be going in radial direction while they are deploying. This will be dragging this sail. So that's how this deploys. And let me look at another example where this is the NASA JPL Starshade project. The idea here is to observe the planets around in the other galaxies. But the main problem is these are basically orbiting around sun or a star. So the light emitted from the star is so bright that you cannot see these. So the idea here is what they call the shade. So you shade the starlight coming from that, and so that the camera or the telescope can see the planets around. So let me show you a small video clip. So you have the original structure compacted here, and it separates from the spacecraft, and then the spacecraft rotates so that the telescope is pointing towards the star. And then once the structure or the star shade is fully deployed, it will go away at a certain distance from the telescope so that it will just cover the sun or the star, so that you can see the planets moving around it. Then if you think about again, now these are very large structures that we are talking about. And then how it will fit into a launch vehicle. Now as you can see here, it's too big for the rocket. So all of us know about art of origami. So you can fold these things, do your trials with papers. This is actually a JPL. And then you can come up with a prototype, maybe a larger scale, and then finally you send it to space. So if you look at this particular structure has two configurations, or two structures in a way. Now what you're seeing here is some sort of a membrane type of a structure. If you can have a look here, I have a paper model where you basically, if you pull from two ends, this can deploy. At the same time, if you release, it will go back and fire. So there's a membrane part of this structure, and then of course, like the umbrella, you have to have some sort of a structural configuration. So today, what I'm going to focus more on the structural configuration. So I'll take two examples and go through that, walk you through that. And so the DLR boom, or the German Aerospace Agency carbon fiber reinforced polymer boom, as well as the MASIS, or the MAS sort of three booms that the European Space Agency sent out. So let me take the MASIS booms first. So the concept here, as I mentioned before, you make slots and put it in a cradle, and once it goes into space, it has to deploy. So now if you look at this, it is folded here, and one by one it has to come out. And also this is a dynamic deployment, so it might go around, hit some part of the structure, so you have to, well in advance you have to know what is going on. So remember now the original title said beyond gravity, and you would assume that it's a one less equation to solve, but the practical problem is this will be operation in space, but how you test them on Earth? Can you really do that? So now before I go into gravity, there are additional problems. Now what you are seeing here is the same boom. Now you need 40 meter long or at least 20 meter long space. So what they are doing is actually what they call the helicopter test. So you hang from a helicopter and